Hey there, 2200. Welcome to this session of our virtual lab. We're going to do experiment 5 together, magnetic fields, and ultimately we are trying to measure the Earth's magnetic field and then compare it to its actual value. It's going to be an order of magnitude comparison, and that's okay. And the reason being is that the Earth's field varies in direction and magnitude depending upon your location. Not only that, it's going to be influenced by external factors, like for instance these cabinets are made of steel. If I walked around this room with a compass, magnetic north would deviate from true north depending upon what equipment I'm near. So I will set up the main portion of our experiment in the center of this room, and that'll eliminate some of this background noise. In fact, if we were at Cal State LA in the Biological Sciences building, of course we would have the same challenges, but even far worse than here. There's less metal and steel in this room than that 3-story building, so we're gonna be good. Before we get started, well, you should read your lab manual. Although this is a fairly easy lab in that there aren't very many measurements to take, the concepts in mathematics isn't trivial. So what you want to do is read your lab manual and understand it the best you can before we get started. Right there is a picture of figure 8. That is the circuit that we're going to build for the first part of our experiment. So let me go ahead and talk about some of those components there. You'll notice that there are 2 resistors, an 11 ohm and a 22 ohm resistor, and they are variable resistors. This here is a variable resistor, the kind that we're going to use today. The 11 ohm resistor is going to be used as a constant resistor. We're not going to vary it. So we're going to plug in to these 2 ends here, and the length of the resistor is going to be constant. It's going to be at 11 ohms. And the other one we have, it's a 22 ohm variable resistor. Part of our circuit will be connected to this prong and this prong over here, which means depending upon where we slide this top slider, it'll give us a different resistance, and in turn give us a different voltage across these 2 plugs. So we're using this rheostat as a voltage divider. Let me put you on pause and I'll talk about the double pole, double throw switch, which is this guy right here. This is pictured in your lab manual, and usually students are a bit confused on how to hook this up and how it works. I think most of the confusion lies in the fact that the switch across here is not connected. And I think intuitively, when someone first looks at this, they think that these 2 ends are connected together, but they're not. This lever here connects this prong to this prong when it's over there to our left. When we switch it down to our right, these 2 prongs are connected. Likewise on the other side. But just bear in mind that these 2 prongs are independent of each other. They are not connected, unless we intentionally connect them. But as it stands with this switch, nothing is connecting these 2. So let's get an overhead view of our circuit and talk about that a little bit. Okay, let's focus for just 1 minute on this part of the circuit. So forget about this here. I just have this connected, which is a very simple circuit. I have a power source connected to 2 resistors. Those 2 resistors are connected in series. So that's what I have here. And forget about this guy for now. That's just a digital voltmeter. It's not hooked up to anything. Here's our power supply, It is on 6 volts, and the positive terminal of that power supply goes into this resistor, comes out here, goes into this one, comes out here, then goes back into the power supply's negative terminal. So I am going to get a voltage across this 11 ohm resistor, and what I'll do is I'll measure it real quick. And I'm getting 1.9, well, to two significant figures, I'm getting 2 volts. Actually, it's showing negative, but that is just the way I plug these in. If it was the other way, it'd be positive. So let's check out this guy here. This is showing 4 volts. So if I connected one of these here and another to this prong, the very 2 prongs that we are going to use when we complete this circuit, let's see if you can see that. One prong here, and the other prong is here, which is connected to this slider. I am able to vary the volts. When I'm all the way across here, the voltmeter reads 4 volts. As I go down, the voltage across these 2 prongs decreases. Now it's at 0.9. I could keep on going down, and I don't know if it'll hit 0, but now we're in the millivolts. So it's 2.2 millivolts, or in other words, 0.002 volts. So we're pretty close to 0. So this here, when used in this fashion, acts as a voltage divider. So by moving this during our measurement, I can control the voltage across this circuit, and in effect control its current. So let's hook up that double pole double throw switch. I'll put you on pause. So here's the circuit diagram in figure 8, and to motivate the reason why we even want to incorporate the double pole double throw switch, let me say a few words about this portion of the circuit. Here's my tangent galvanometer hooked up to my ammeter, so I could know at any given time how much current is going through that galvanometer. I want to, at will, be able to switch the direction of the current. So in one portion of the measurement, I want the current to be flowing down, and then in the other, up. So the double pole double throw switch serves that purpose. I just switch it to the left and to the right and alter the direction of the current. Now, to make it easier to understand, I highlighted 2 different areas. One of them is highlighted in pink, the other in yellow. The pink highlighted area represents the switch when it is thrown to the left or up position. The yellow when it's thrown to the right or down position. So I have some current and it's moving in this direction. Let's say the switch is in its up or left position. When the current gets to this point here, it follows the connected path, which is that of the pink highlighter. It comes over here, then crosses the switch diagonally, and at this point it runs down and then up through the galvanometer, right through the ammeter, back down here, diagonally across the switch. It follows this pink path down here, then back to the power supply. So let's say I switch the double pole double throw to its right or down position. In that case, the current again is coming in this direction, follows this path here. When it gets to this point, it doesn't go to the left because that pink highlighted region is not connected. Instead, it follows the yellow highlighted region, so it goes to this point here. In the previous case, it went diagonally, but in this case it doesn't because that pink portion is not connected. So right here is like a dead end. So instead, it goes up through our ammeter, and this time goes down the galvanometer, comes around here, goes through that yellow highlighted portion, then comes down here through this wire and back to the power supply. So what we need to do is hook up our switch to match that diagram there. Here's our switch. Let me zoom out. I need these two prongs connected as depicted here. So that's as simple as getting a Pomona lead and making those two connections. I also need the other two diagonal prongs connected to each other. If you can't see the figure too clearly, you could look at your lab manual. So this switch is connected diagonally as it is in the diagram. And when the switch is in this position, it's an open circuit. The wire that is coming off that variable resistor is going to be plugged into the center there. And on the bottom of the switch, this center plug here is going to be connected in turn to the bottom of that resistor and the power supply. These two prongs here are reserved for the galvanometer ammeter section of the circuit. So once I have that other part set up over here, they're just going to plug into these two prongs. Now, what I was going to do is get a similar lab bench like this and move it to the center of the room, but as it turns out, since this is made of steel beneath this wood and there's a bunch of tools in it, it's drastically affecting the compass. It is almost pointing in the opposite direction. So I'm gonna have to find, I'll use a plastic cart and set that up in the center of the room, and we'll start taking our first measurements. So let me put you on pause. So our complete circuit is set up. What you are looking at right now is the second half of that circuit, which is the tangent galvanometer and the ammeter. Well, and you can see the switch as well. What I want to bring to your attention is that I oriented the tangent galvanometer such that the compass needle that points north is parallel to the plane that those coils on the tangent galvanometer are. So there's no current going through the galvanometer right now, so there's no induced field, magnetic field created by the galvanometer. So that compass right now is just pointed to the Earth's North Pole. Now, if I turn on a current, the needle should deflect from the north, depending, of course, in which direction the current is going. So in one direction of current flow, there'll be a magnetic field in this direction. If I switched the direction of the current, the field in the center of this loop would be in the other direction. So let me go ahead and flip this switch. You could see from our ammeter that a current is indeed running through our circuit, and you saw the needle move. Now, it didn't move much. Well, it moved about 21 degrees. What I can do is adjust with our potentiometer the potential across this circuit. So if I increase the potential, I'll increase the current. So I'll do that now. You could see the needle moving. It's deflecting further and further away from north. So let me keep going. Let me lower it a bit. Right now it's around 60 degrees from north. Now I'm going to turn off the current. And what I'll do is I'll see where that needle goes if I put the current in the other direction. And as I mentioned before, because I don't have a digital ammeter that measures current in both directions, I'm going to have to switch those two plugs. Now, double pole, double throw switch will be turned in the opposite direction. And you can see the needle is deflected from north again, but in the opposite direction. So it is about 30 degrees, which is symmetric with the other case, right? In the other case, it went 60 degrees from north, and now it went in the other direction. So we're going backwards. 60 or 360 degrees minus 60 is 300. So you could see it deviated from north 60 degrees in both directions. Now what we want to do is adjust the current so that a magnetic field is produced from that tangent galvanometer such that the needle is deflected at the midpoint between north and the field that this tangent galvanometer creates. So that would mean we need to find the current that makes that needle go to 45 degrees. So let me turn off the current here, and I'll start in the other direction. I'm walking over to the potentiometer, and I'm decreasing the voltage. So I don't know how well you can see the needle. Well, you could for sure see the needle. I don't know how well you could read it. So you'll have to take my word for it. Right now we're in the area of 45 degrees. Let me see if I can fine tune it. Right there looks about good. It looks like, let me increase it just a tad. That looks to be about 45 degrees. Now let's see if, once we reverse the current, if we are 45 degrees in the other direction. So what is 360 minus 45? I'm gonna say 315. And we look to be at 310. So it isn't completely symmetrical. How many amps are we reading? 1.9. Of course, we're on the middle scale, so we'd have to divide by 10. So we are at 0.19 amps. .19 amps in the other direction. So the current seems to be equal in both directions, but looking at the compass now, I'm a hair above 45. Let me adjust this a little bit more. Let me see where I am on the other side. So we're a hair above 310, but we should be at 315. Now, instead of spending our time trying to figure out why this isn't actually symmetrical, well, it could be caused by a number of factors. Let me just say this. Before I did this segment of the video, our tangent galvanometer was on the edge of this cart, and this was on the edge of the cart. When I put the compass in that tangent galvanometer, it was not pointing at true north, even with no current. So just by virtue of this compass being near the edge of the cart, the field was totally distorted or being influenced by external factors. The edge of this cart is made of metal. The only thing plastic is in the center. So basically what I'm saying is that there could be a number of reasons why in one direction I'm getting a field that's strong enough to point that needle exactly 45 degrees away from true north in one direction, but when I reverse the current, it goes to 310 rather than 315. The field is a bit different in this area here. So this looks good to me. What do we have? I am reading 1.8. I'm sorry, we are on the middle scale here. So actually we are at 0.18, 0.18 amps. .18 amps, and that looks like it's a wrap. Let me put you on pause and we'll do the next part of the experiment. Okay, after I disassembled the circuit, I realized there are a couple of pieces of information you're going to need for your analysis, one of them being the number of coils in this galvanometer. So for this unit, there are 3 different configurations you can use. If you plug into these 2 ports here, you'd be using 5 loops. Plugging into these 2 uses 10 loops, and plugging across these outer 2 utilizes all of the loops in this coil, which is 15. The other thing you're going to need is the radius of those loops. Now, I'm not going to bring a ruler up to this and zoom in on it. Just take my word for it. I measured it and the diameter is 20.4 centimeters. That would be the diameter. All right, let's get back to our experiment. Okay, in the last segment, we were able to use an ordinary compass and determine the direction of the Earth magnetic field by placing it in this region here. But that only gave us the direction of the field in the horizontal direction. What we want to do now is figure out or measure what the true direction of the magnetic field in this region is. So we're going to use this dip needle. What we do is position it so that the needle is pointed north. And what I did was I moved the base so that the arm of this base is aligned with the needle. And now I'm going to rotate this. Okay, so I want to do this without disturbing the base. And I want the needle perpendicular to the surface of the Earth. And this is going to give us the true direction of the field. I'm going to put you on pause and change the angle of the camera. So here's the final configuration of our dip needle. Not only do we know the field points in this direction, which is north, it also dips downwards. So the field isn't perpendicular to the Earth's surface. Anyway, it is not at this location. It dips downwards, hence the dip needle. So you're not going to be able to read this, but along the horizontal we're at 207 degrees. So 207 degrees, according to this scale, is along the horizontal. The needle is pointed at 338. So this is 270 and the needle is 338. So you'll use that to determine, well, I'll leave it up to you. This concludes the segment with the dip needle. So here you go, a bar magnet suspended from a string. What we're going to do is set it into motion and determine its oscillations, or its period of oscillations. Now, when I've set these up before in the past in the lab, I got 6 stations, all those magnets are hanging from the ceiling, and within a short period of time, well, I never timed it, but it didn't seem like it took too long, they're all completely stationary. They all eventually come to rest. But this particular magnet here is not coming to rest. It's been a while. I don't know if it's tied. I don't know if there's vibration in my ceiling or what, but it's not stationary. Good thing is it seems to be oscillating 10 degrees from equilibrium, which is what we wanted to do. It's slightly less than 10 degrees. 10 degrees isn't much, as you can see. What I think I'll do is just start timing it now. So let's see. -1, 0. Okay, I messed up with the timer. -1, 0, 1, 2. I'm counting out periods. 3, 4, 5, 6, 7. So I counted out 7 periods and it took 42.3 seconds. 42.3 seconds to go 7 periods. So there's your data. So for part B, there are 2 other measurements that we need to take. One of them is the length of the magnet. So this bar magnet is 15.2 centimeters. Now, it may not look like the north end is right on the 0 from your vantage point, but that's just the angle the camera is in. Trust me, it is at 0. So 15.2 centimeters, or 15.20 centimeters. And I'm going to put you on pause and go grab a digital scale. Here's another piece of data you will need for your calculations. That is the mass of the magnet, which is 90 grams. All right, let's get back to the rest of the experiment. Okay, on to part C. This is the last part. What I did was I placed that compass in the same position that it was previously located at. Well, it's about lower, a little bit lower in space. It sat on that little plate on the tangent galvanometer, but it's centered in the same position. I have it on a ruler. The center of that compass is right over the 90 centimeter mark. You could probably see a monster can there. That's just balancing the ruler because I'm going to ultimately rest a bar magnet on top of that ruler. And if that can wasn't there, it would catapult that compass. So I have my bar magnet and I'm going to move it towards the compass. Now you could see that the compass is now pointed west. The strength of the field created by this magnet in this direction is so strong that that compass doesn't really feel the Earth's magnetic field. That needle is pointing in the direction of the field that this bar magnet is creating. So the point of this portion of the lab is to, well, I'm not going to tell you the point. I'll just go through the motions as to what we're trying to accomplish and measure. I want to put this bar magnet close enough to that compass so that the needle deviates from north at 45 degrees. So that it should land on, what was that, 315. So right now it's at 320. I'm going to place it gently place it on the ruler. And I don't even know if I should mess with it. I mean, it's pretty dead on, almost. I could move it a tad closer, which I'll do. We're gonna leave well enough alone. I'm leaving it there. Now, the bar magnet is out of frame, but it is simply just resting on that ruler. And the tip of the bar magnet, the north tip, the tip closest to the compass, is 35.9 centimeters. 35.9 centimeters. And the center of this compass, as I mentioned before, is right on 90.0 centimeters. So use those measurements to determine the distance in question. Now, to avoid any mistakes, let me just give you a hint. You are going to need the length of that bar magnet for this calculation. Don't just simply measure the distance between the end of that magnet to the center of the compass. Let me put you on pause.